microscopy as well as spectroscopic investigations. So, let's go.
Can you see my screen?
Yes.
Yes, okay. Thanks, George, for the introduction. So as you said, yes, in this part of the webinar, I will focus more on the spectroscopy side, and also I will show some possibilities with respect to in situ and in-operando investigations in TM. Well, structure physics is the group that is in charge of the transmission electron microscopy activity at the University of Oslo. We belong to the physics department, but we are also part of the Center for Materials Science and Nanotechnology, or the so-called SMN. As you can see here in this schematic, practically SMN, it is an interdisciplinary collaboration among 5 research groups in physics and chemistry department. So we collaborate with the semiconductor physics group, with nanostructures and functional materials, with catalysis and electrochemistry groups. And exactly this collaboration defines a lot our activity and explains the wide range of energy-related materials that we study for sustainable energy solutions. These are some indicative application areas as solar cell technology, high-power electronics, batteries, hydrogen storage, fuel cells, thermoelectrics, and quantum technology. Of course, our activity is in line with the societal challenges comprised by the UN Sustainable Development Goals, such as the affordable and clean energy, industry, innovation and infrastructure, sustainable cities and communities, and climate action. Of course, you know that the potential of energy materials can be completely explored by fully understanding their fundamentals. And in many cases, atomic scale information is required. So this can be provided by transmission electron microscopy. Here you can see an image of our state-of-the-art microscope in our lab. It is an FEI Titan G2 operated at 60 and 300 kV. And it is probe-corrected and monochromated, meaning that we can reach high spatial and energy resolution. Also, in this simple schematic, you can see the possibility that we have to use multiple detectors simultaneously. So we can take advantage of the complementary information that we can extract through the different mechanisms of electron specimen interactions. For example, for imaging in STEM mode, we can use different detectors. For example, if we collect electrons that are scattered at high angles, we can have pure Z contrast images. Then we can start introducing diffraction contrast, and with angular bright field at very low collection angles, we can visualize both heavy and light elements. Along with the structural information, we can also have chemical information by combining spectroscopies as EDX and Electron Energy Loss Spectroscopy. In this talk, I will focus more on EELS results, since EELS it is more sensitive to light elements. It has superior spatial resolution than EDX, and also it gives access to bonding information. And with low-loss EELS, we can also extract important information, such as about the electronic properties of our materials. Furthermore, the lab is equipped with sample holders for in situ and in-operando experiments, so we can expose our samples to precise heating, electrical biasing, and different gases. Also soon we will have a closed cell liquid holder. And we can perform in-operando studies. Basically, we can build with the help of nanomachining and micro-manipulation by focused ion beam, nano-sized devices on chips and run an in-operando study on the nanoscale. So with respect to EELS, I will give you an example from an extended work that we did on studying defects on semiconductors. And for the in-situ and in-operando part, we will focus on battery materials. So starting with the defects in semiconductors, it is well known that point and extended defects, as well as their interaction with dopants, have a direct influence on semiconductor properties. So we need to precisely identify different defect types and also understand their formation and evolution in order to master semiconductors. Here, we will focus on an example of zinc oxide, which is a wide and direct bandgap semiconductor with potential applications in optoelectronics, quantum technology, spintronics, and radiation sensors. The motivation that triggered our study is the doping asymmetry that zinc oxide exhibits, where only N-type conductivity can be readily accomplished. Nitrogen, which is the most promising candidate for P-type doping in zinc oxide, exhibits very contradictory results so far, hence reliable P-type doping is still a challenge. Furthermore, nitrogen-doped zinc oxide exhibits a remarkably different behavior in terms of defect evolution. It has been previously reported that zinc vacancy clusters are extremely stable even at higher temperatures, and this happens only for the case of nitrogen dopants, and also they showed the generality of the phenomenon, meaning that it is irrespective of the growth and implantation methods. And also, it has been reported a reverse thermal evolution of defects, meaning that there is a dramatic increase in defect concentration after annealing, and this happens again exclusively for the case of nitrogen implants. So the exact mechanisms behind this weird behavior is not understood, and detailed nanostructural and chemical defect characterization is of utmost importance. In order to understand what happens, we did a very fundamental approach, studying nitrogen-implanted zinc oxide single crystals, and then we moved to applications to zinc oxide gallium nitride quaternary alloys in the form of thin films for applications in photovoltaics and solar water splitting. Now, I start with the fundamental study that we did in nitrogen-implanted zinc oxide after annealing. Here you can see two images recorded simultaneously in medium magnification, and you can already understand the importance of the complementarity of using different detectors for imaging. For example, in annular dark field, due to the intense diffraction contrast, we can easily see the localization of extended defects. While with high-angle annular dark field imaging, due to the Z contrast, we can easily see the localization of clusters of lower atomic density. The first step was to do structural analysis in order to understand what types of extended defects we had. Again, here you can see one example of high-resolution images along these defects. You can see again how useful is the complementary information that we gain from different detectors. In HADF, we can see the atomic columns only of heavy elements, of zinc in our case, while in annular bright field, we can visualize both zinc and oxygen. So you can see that in aberration-corrected microscopes, we can easily resolve the zinc-oxygen double, and this helps us to follow the stacking sequence and to see easily what violations we have of the stacking sequence. And also imaging in that mode helps a lot to see if we have changes of polarity in the case of polar materials. We characterized many different stacking faults. So this was a prismatic stacking fault of Ameling's type. I will not insist in all the structural work that we did, but I will focus more on the spectroscopy side. And the main question here, as I said before, was to understand what happens with nitrogen. And since nitrogen is a very light element, EELS spectroscopy, in contrast to EDX, it is the appropriate one for this detection. So working along these nano-sized clusters, you can see at first place an intensity ADF map and the corresponding relative thickness map acquired by low loss seals. We can see that we have a drop in the intensity. So this is an indication of a depleted area of a zinc vacancy cluster. You can see the size, it is only 2 nanometers in diameter. And then by extracting the 2D maps with core loss seals, this is the nitrogen K peak, you can see that we had nitrogen signal only inside these zinc vacancy clusters. And then it was abruptly disappeared outside this cluster. So we have localization of nitrogen exactly in this zinc vacancy cluster. Furthermore, by comparing the shape of and the fine structure of our nitrogen K peak, we understood that we have formation of molecular nitrogen. So the zinc vacancy molecular nitrogen defect was identified, and you can see already that it is important that we have simultaneous information of the structure, of chemical information, and bonding information, and this helped a lot in order to develop the defect evolution model in this system. So practically we proved that nitrogen in the oxygen substitutional site is not a stable configuration, since bonds between zinc and nitrogen were never detected. We have the formation of molecular nitrogen, that it is trapped by these zinc vacancy clusters, and this phenomenon by itself can explain the exceptional thermal stability of these clusters that was reported before. Then this phenomenon suppresses the recombination of zinc and oxygen interstitials that all condense on the basal planes and create this all these stacking faults that I showed before. And this also explains the reverse annealing phenomenon and the dramatic increase in the defect concentration even after annealing in this system. Now, after having this very fundamental understanding of the behavior of nitrogen and how it affects the defect evolution, we moved to the study of thin films of zinc, oxy, gallium nitride alloy. These films are ideal for bandgap engineering. You can see here the bandgap diagram. Zinc oxide and gallium nitride have very similar bandgaps. It is 3.3 for zinc oxide and 3.4 for gallium nitride. However, due to a band bowing effect, when alloying those two materials, we have a significant bandgap reduction. And of course, we can tune this bandgap by only changing the composition of the alloy. Now, to cut the long story short, after annealing, exactly the same phenomenon was observed. You can see here an image of a part of the thin film, and we observed along the grain boundaries and threading dislocations the formation of these nano-sized voids. You can also see here that they were, the larger ones were taking a very faceted shape. And with EELS spectroscopy, again, we proved that these nanovoids were trapping molecular nitrogen, while nitrogen and gallium bonds, as you can see here, the changes in the shapes of EELS spectra, these bonds were detected in the rest of the film. So a main question for us is to understand if this redistribution and rearrangement in the nitrogen bonding can affect the bandgap properties, the bandgap values of our fields. In this case, low loss EELS was very helpful. We performed on the nanoscale bandgap measurements with low loss EELS. At first place, you can see a comparative study that we did, first measuring the bandgap in pure zinc oxide, and then by comparing films with different gallium and nitrogen concentration, you can see that by increasing the concentration, we have gradually a reduction of the bandgap. For 15%, we reached 2.5 eV. Now, the next question was to be sure that this bandgap is stable, has a stable value throughout the whole thickness of the film. And you can see here part of the thin film and the corresponding 2D bandgap map. It was important that we found that there is a homogeneous signal distribution. Hence, this means that the apparent bandgap that we measure here in overall, it is a result of a homogeneous alloy and not an average of a mixture of different phases. And with that, I stop with the spectroscopies. I think it is very clear that by combining core loss and low loss EELS, we can define structural, chemical, bonding changes, and also we can correlate that and check if they have an impact on the optoelectronic properties on our materials. Now we will move to the in-situ and in-operando part, and as I said before, we will use an example from battery materials. It is well known that in the past 3 decades, lithium-ion batteries have pervaded almost all portable electronics, such as smartphones, laptops, tablets, tools for personal care, also all electric automobile vehicles, and all parts, all segments of energy storage market. However, the growing global demands for large-scale energy storage and for safer battery technologies has intensified research towards all-solid-state lithium-ion batteries. Hence, by replacing the flammable organic liquid electrolytes by inorganic solid electrolytes, all solid-state batteries can be chemically safer, compact, faster recharging, and they can operate at higher temperatures. EMCINS is a new material, a new two-dimensional material. It was discovered just in 2011, and it is very promising as an anode material for all solid-state lithium-ion batteries. EMCINS are metal transitions, carbides, nitrides, and the lightest ones, the lightest carbides, exhibit the potential to replace and supersede the properties of the most common 2D battery anode material, which is graphite so far. The problem with EMCINS is their synthesis route. So far, they are developed only by following top-down synthesis by chemical etching. Basically, they do chemical etching. They etch away the metallic layers of their max phases. But this process results in these residual surface terminations on functional groups. And this is an unavoidable byproduct of the etching process, and it has, unfortunately, detrimental impact on the properties of this material as anode for batteries. So what we need is to follow bottom-up synthesis routes. And so far, the whole thing is in its infancy. Basically, the only EMCIN that has been synthesized with a bottom-up approach is molybdenum-2 carbide by CVD. So there is a lot of space to learn, and we need to learn many things with respect to the atomistic factors that govern the growth mechanisms of enzymes. And our idea was to try to do what we can do with transmission electron microscopy. And basically, the question is, can we do growth of enzymes in situ, in TM? Practically, we would like to imitate the CVD process in TM. So here you can see a schematic of the process followed by CVD, and this is what we want to follow in TM. If we want to grow molybdenum to carbide, practically we need to have a bimetallic layer, a molybdenum substrate covered by copper foil. Then we need to heat it up so copper will get liquid, and it acts as a catalyst for molybdenum to diffuse. And when it reaches the surface, then we need to have the carbon source, which is methane in our case. So molybdenum at the surface will react with carbon, and then finally we will have the formation of 2D nano-sized flakes of molybdenum carbide. So what we did step by step to achieve in situ growth in TM, the sample preparation was a tricky part. You can see here that we had these two metallic foils, molybdenum and copper on top. We heat it up, so you can see here, or even better here, that copper was melted, covering the whole substrate. Here you can see a cross-sectional SEM image. And with the help of focused ion beam, we managed to take out a very thin sample of the interfacial area. We further thinned it down. So this part, you can see here, it is an electron transparent region. And then with, again, with FIB, we managed to successfully deposit our sample on any chip for TM. These holes here are the electron transparent areas of the chips. And then the funny part started for the in situ TM experiment. Practically, we want to have an in situ gas heating experiment. So this is what we, the things that we control when we do the experiment. From one point we can see, this is a digital micrograph software, we can see what happens to our sample on the nanoscale. And also in another software we can monitor, we can control the whole process, we can insert different gases. Also, we can increase the temperature. We can go up to 1000 degrees. And also, we can change the pressure of the inserted gases. We can go up to 1000 millibars.
5 minutes, please.
Yes. So you can see here what we see in the beginning, how our sample was before the reaction. And now here we inserted methane and started heating up. So you can see that gradually we have changes. And then we reached the regime, the values that are suggested by the CVD process. So the temperature, we reached the highest temperature and the highest pressure of methane. And you can see that we started having this nice formation of flakes. Some of them were micro-sized, and also we had nano-sized flakes. Also, what it is important to see is that even at the highest temperature, at 1000 degrees, the system, it is quite stable, so we could also acquire high-resolution images. Here you can see that we can easily see the lattice fringes. You can see also the FFT of these nano-sized flakes. So here is a summary of what happens before and after the in-situ gas heating experiment, you can see that we have the formation of nice hexagonal flakes, nano-sized flakes, and also with high-resolution imaging and with EELS spectroscopy, we verified the structure of molybdenum-2 carbide. So the first challenging part was successful. We managed to do in-situ growth in TM, and this is an alternative way, let's say, to use TM nowadays. Of course, the next steps, this is a project, an ongoing project, will be to control the growth. We want to start growing just a few monolayers of MXenes in order to understand the atomistic factors governing the growth mechanism. And this is my last slide. Again, one of the next steps will be to perform in-operando experiments. Again, the same idea is to use FIB, but this time we will build all parts of the battery, a full battery, on a dedicated chip. So we will run an in-operando study. The goal will be to see how stable are the electrolytes and the electrodes during the cycling process. What happens with the interfaces, because the interfaces are a big problem for all solid-state batteries, if we have formation of defects, if they trap lithium, and so on. This is, again, a very challenging and a quite novel step, because so far there is only one group that managed and published doing such a process. You can see here the group of Gong et al. They managed to build a nano-sized battery on a chip with gold anode, and after the in-operando experiment, they studied on the nanoscale the formation of different defects and how they and if they trap lithium. Yes, I think I will stop here. Thank you very much.
Thank you very much, Poppy, for showing us how we can really push electron microscopy and nanoscopy to the limit of the atomic scale, using these huge aberration-corrected and probe-corrected microscopes, and using the in-situ and in-operando new techniques. I can see some questions maybe you would like to answer from Kostas Giannakopoulos. On what sample do you get the nitrogen reference in EELS?
Yes, one of the molecular nitrogen, because let's go back. I remember, okay, this reference, number 2, was from the literature. It was another group that they were studying the formation of molecular nitrogen. So we asked them, and we took it from them. I don't remember the name, but it is a reference in my paper. For the gallium nitride bonding, I had a pure gallium nitride sample. And of course, with respect to the bonding of nitrogen with zinc, we were asking to have a zinc nitrogen sample, but we were informed that it is an extremely thermodynamically unstable compound, and it's very hard for people to grow zinc nitride. And this, of course, it is already an explanation of the phenomenon that we see. Nitrogen doesn't want to bond with zinc.
And there is a question from Zenia Simeonidou. What is the role of hydrogen in the pre-mixed gas, and in which percentage is it used? Yes,
hydrogen basically it is used as a reducent carrier gas in the process, and the percentage was low. We had only 1.5% methane into hydrogen. I didn't highlight that. Yes, it was, we don't insert pure methane, we insert a mixture of methane and hydrogen in the system.
Okay, so thank you very much.
Thank you.
I will skip my own questions. I have many, but I don't want to delay.
Okay, we will have another meeting.
And so